Okay, now we want to talk about the mechanical properties of minerals. And the first mechanical property is the hardness. And this is related to the strength of the bonds that are holding the atoms together to make the mineral. So some of the bonds are stronger than others. And so some minerals are very easy to break those bonds. And so the hardest mineral is diamond. And so we have a special scale, the hardness scale, that goes from 1 to 10. So 10 would be the strongest mineral, and that would be diamond. And then 1 is going to be the least hard, and that's going to be talc. And so what do you use talc for? Talcum powder. And talcum powder is very soft. And you can see that there are different hardnesses for different kinds of minerals. And remember that let's say diamond is a 10, so that means it could scratch corundum, which is a 9. And corundum, in turn, could scratch quartz, for example, which is a 7. On the other hand, if you were to take quartz and try to scratch corundum with it, it wouldn't work. Also, you'll notice that there are shorthand ways of estimating the hardness of something by either using your fingernail or by using a copper penny or by using a nail. And so that also gives the hardnesses of some of those other minerals. All right, the next thing we want to talk about is going to be tenacity. And so this is how does a mineral respond to force. So if you recall, in an earlier lesson, we talked about what a force was. It was a push or a pull. So if you were to take a mineral and start to apply a force to it, what would that mineral do? Well, some minerals are going to be elastic, and they're actually going to bend. So for example, mica is a mineral that bends whenever you apply a force to it. There are some minerals that when you apply a force to them, they will begin to flow like a liquid. And so an example of that is copper. And this is the reason why you can take a piece of copper and you can bend a wire with it and you can use it in that way. But other minerals, if you apply a force to them, they're going to break. And one way that they break is that they will break along certain lines of weakness in the mineral, and then that's going to produce different kinds of faces of the mineral. And so that's going to be called cleavage. Okay, and then but there are other kinds of minerals that their bonds are equally strong in every direction. So that means that when you go to break one of those things, they do not break along nice faces, and they have what's referred to as a conchoidal fracture. So an example of this would be quartz. If you've ever taken a Coke bottle or something and accidentally dropped it on the ground and it shatters, you'll notice it makes these kind of curved edges to it. So it doesn't break along nice faces when that happens. And that's a feature of quartz. So what do these cleavage faces look like? So here is a picture that shows that sometimes the cleavage faces can be perpendicular to each other. Sometimes they can be at an angle to each other. And so you have different kinds of cleavages. And you can just look at that just to see how that they look. A cleavage plane is not necessarily the same as the crystal face. So you might get the idea that a crystal face is the same thing as a cleavage plane, but it's not. Remember that the crystal face is a result of atoms individually attaching to the crystal, making this repetitive crystal order that has certain edges to it, which we call the crystal face. On the other hand, the cleavage are planes of weakness when it breaks. So it's a relationship to the strength of the bonds that are inside that particular crystal. So in case you're wondering, how can you tell the difference between crystal shape and cleavage? So crystal faces are normally smooth, whereas a cleavage plane are commonly broken up into stair-like fashion. Some crystal faces have fine grooves or ridges on their surfaces, whereas cleavage planes do not. So an example of this would be striations. When we look at feldspar, for example, plagioclase feldspar is going to have these striations on the crystal face. But if it's a cleavage plane, it's not going to have those lines on it. And then also, when you drop a mineral, and in lab, please do not drop the minerals, but if you were to drop the mineral and it breaks, it's going to break parallel to, will not break parallel to crystal faces. It will break parallel to the cleavage planes. Okay, let's take a break, and when we come back, we'll talk about yet another property of minerals.